All right, we're going to skip over section 2 in chapter 2, and we're going to move forward and talk about section 3, where we talk about graphing linear equations or linear functions. Now, in this particular section, we're going to basically talk about what a linear function is, and then we're going to graph them using both a table, intercepts, and slope-intercept form, and kind of talk about input values and output values a little bit more, like we did last week when we talked about functions. These are some key terms that are going to pop up as we move through this. Most of us should be familiar with a lot of the different terms that show up here. The one in particular that we might not be super aware of would be this one down here. All right, we talk about y-intercepts a lot, but we don't talk about x-intercepts a lot. The general idea is the same. We're just looking at a different part of our graph or a different area of the coordinate plane when we're talking about x-intercepts. The first example, or the first thing that we're going to kind of look at, is how do we identify whether or not something is or is not linear. This just presents an example of where something like this might be used in a real-world situation. In this case here, we're monitoring a hurricane that happens to be off the coast of Florida. Specifically, after a certain number of hours, what is its distance from the coast? All right, so if we move forward here and we look at the information presented to us, our top row would signify our input values. In this case, is going to be representing time. The bottom row is going to represent our distance from land. Now, as you can see, this is already drawn out for us a little bit, but we want to measure the changes in both our input values versus the changes in our output values. If those changes are constant all the way through, like in this case on the top, we are constantly changing our input values by 1. On the bottom, the resulting output values are always changing or basically dropping by 25. In both cases, they're constant, so we can be sure that this is a linear function. All right, now eventually we're going to work forward to the point where we're able to tell what a slope is based on those changes also, but we'll get to that here in a second. Most of us should be familiar with this form of an equation in here. Now, you might typically be used to seeing that as y equals mx plus b, but remember when we were talking about functions earlier in the year, functions really aren't any different than the equations that we talk about. They just meet a specific set of guidelines that allows us to write them in function notation or allows us to refer to them as functions. All right, so keep that in mind as we move forward. The whole idea hasn't changed. The notation might just be a little bit different. So here's an example where we're given input values versus output values, and we need to determine whether or not these values represent a linear function. So just like the example with the hurricane, I'm going to take a look at the changes between my input values. As we move over, I'm going up to, or I guess I should say I'm increasing by 2, not necessarily going up. All right, so we're constant on the top. On the bottom, I'm going to look at my output values. Same general idea here. As I move through the output values, I can see that they are increasing by 1 each time. So in this case, both the top and the bottom are constantly increasing. So I can say that this is a linear function. I'm going to take a look at another example here. Same idea. If I look at the differences or the changes in my input values, they are increasing by 1 all the way across. Now, if we look at the bottom, and most of us can probably identify this without me even going through it, but as I move through my output values, we can see that I start by increasing by 2, then I'm increasing by 4, and finally I'm increasing by 8. All right? Just like the last one, they are increasing specifically on the top at the same rate. But on the bottom, even though they're increasing, they are increasing at different rates. All right, they are not constant on the bottom, or they are not consistent. Because they are not consistent, that tells us this is not a linear function. And basically, this would probably be a better example of something that is quadratic, or something that involves an x squared somewhere along the line. Now, you didn't have to know that. It's something that we'll get into later as we progress forward in the year. But just kind of gives you an idea of the different types of functions and what they can present to us. Most of us should know what slope means. Right? When you're given a graph, we can identify the slope by looking at the rise of the graph versus the run in the graph, or how much does it go up versus how much does it go over. All right? That can also be represented by the change in your y values versus the change in your x values, or in the case of talking about functions, the change in your f of x, or basically the change in your output values versus the change in your input values. Now, we're going to talk a little bit further on down the road how to actually calculate slope if we're given 2 points. But for right now, we're just going to use it to help us graph some lines. All right, so if I'm given a situation like this where I don't have an actual function that's given to me in terms of, f of x equals 3x plus 4. I'm just given a slope and a point that the line goes through. I'm going to begin by simply graphing that point on my coordinate plane. Now you'll notice my coordinate plane here has a scale of 2 in each direction, meaning instead of counting 1, 2, 3, 4, we go 2, 4, 6, 8. Now the whole idea of that is just to give us a little bit more room so that we can use larger input values and arrive at larger output values and still be able to fit them on a graph so we can see what it looks like. So if I'm going to graph -1, -3, I'm going to start at the origin in the middle of my graph, and I'm basically going to move -1 in x direction and -3 in a y direction. So to the left 1 space and down 1, 2, 3 spaces and get to a spot right about in here. All right, from that point, I'm simply going to use my slope to find at least 2 more points that allow me to figure out what my graph should look like. Now, remember, a slope represents rise over run, or how much does it go up or down versus how much it goes left and right. A positive slope means that we are going to go up 5 spaces, so 1, 2, 3, 4, 5, and I'm going to go 1, 2 spaces to the right to find my first point. Now, a positive slope also indicates that we could technically have -5 over -2, because when you think about it, if you take a negative and divide it by a negative, you should arrive at a positive answer. So a slope of +5 over 2 can technically mean -5 over -2. So I'm going to go the opposite direction here. I'm going to start at my point, and I'm going to go down 1, 2, 3, 4, 5 spaces, and I'm going to go left 1, 2 spaces to arrive at another point. Now, you don't always have to go or find 1 point that's above and 1 point that's below the original line that you start with. We certainly could have, at this point right here, kept going another up 5 and over 2, but just to kind of show how slope works, I went in both directions. Now I'm going to draw my line in because I have a pretty good indication here of where that's going to go. My line probably isn't going to be 100% straight because I'm not using a straight edge, but you get the general idea of where that graph is going to go. And you can also see as we move along that line, up from this point here, all the other points that particular line happens to go through would also be solutions to that particular function if we were thinking about it from that standpoint. Here's another example. Really the only thing that changes with this example is the fact that obviously I have a different starting point down here as well, but my slope is negative in this case, which tells me that I could have -3 over 4, or think about it as -3 over 4, or even think about it as +3 over -4. Just telling me that my slope allows me to go in 2 different directions from the original point that I plot on my graph. So I'm going to start by plotting 0, 2 on my coordinate plane. So the 0 indicates that I'm not going to move anywhere left or right from the origin. The 2 tells me I'm going to go up. So my first point is going to be right here, directly on the x-axis, 2 units up. Now I'm going to use my slope. I'm going to start with this slope right here and think about the negative 3/4 as negative 3 over 4. So that tells me I'm going to go down 3 spaces. So 1, 2, 3, and then I'm going to go over 1, 2, 3, 4 in a positive direction. Now I'm going to look at this slope here, which basically just tells me instead of going down 3, I'm going to go up 1, 2, 3, and I'm going to move left or negative 1, 2, 3, 4 units to arrive at my second point. Now, if you wanted to find more points than that, you're certainly welcome to. I think 3 is a good number to get a general idea of where our graph is supposed to go. Again, I'm going to draw that line in. It's probably not going to be 100% straight, but again, it gives you a general idea of where that graph goes and what values it would go through. Now, going back to the very beginning, when I talked about some key terms that we were going to come across or key concepts that we were going to talk about, I talked about intercepts. Now, we should all be pretty familiar with the y-intercept, or basically the point at which the graph crosses the y-axis. X-intercept has the same general idea, but instead of talking about where our graph crosses the y-axis, we talk about where it crosses the x-axis. Now, there are certain characteristics of both the x and y-intercept that allow us to use those intercepts to graph a line. Now, the one thing about x and y-intercepts is it's kind of one of those exceptions to the rules where typically we say we want to have 3 points before we graph a line. When you're graphing using the intercepts, you can get away with only having 2 points when you graph your line. Now, when we think about the x-intercept, okay, the x-intercept is going to lie on the x-axis. All right? It doesn't matter what value of x I have, the y value is always going to be 0 for your x-intercept. So what that allows us to do is we can take 0 and fill it into y in our original equation and solve for x and find the corresponding x value that will give us that point. At the same time, it does not matter what our y value is for our y-intercept. The x value is always going to be 0. So the same idea applies. If I want to find the y-intercept, I'm going to fill 0 in for x and solve for y. All right, so now an example of how that's going to work. If I look at the equation I'm given up here, all right, I'm going to start with my y-intercept. Now remember, again, it does not matter what my value of y is. My x value is always going to be 0 on a y-intercept. So I'm going to take that equation I'm given, and in place of the x, I'm going to fill in 0. And now I'm going to manipulate that and solve for y. So in this case right here, 4 times 0, fairly simple. That's going to end up being 0. So I can completely just drop that out of my equation. So now I'm left with negative 2y equals 16. Again, perform the opposite operation like we talked about in the last lesson. Divide by negative 2. Y is going to equal negative 8. So basically, when I input 0 right here for the x value, I get a y value of negative 8. So what that is telling me is my y-intercept should be 0, negative 8, or basically be in this area down here. Now I'm going to take the same idea and I'm going to apply it to the idea of the x-intercept. So in this case, I am going to take 0 and I'm going to fill it in place of my y value. That was kind of a big 0. All right, and that's going to equal 16. So I'm going to solve this one for x and get the corresponding x value that will go with my y value of 0. So again, just like before, in this area, that's going to become 0, which makes this relatively simple. 4x is going to equal 16. When I perform the opposite operation here, the 4's will cancel. So x is going to equal 4. So I have just arrived at the point for 0 as my x-intercept. So I'm going to go over to the right 4 spaces and up 0 spaces to get my x-intercept. And now I've given myself, again, a general idea of where the graph is going to be. Now, again, I'll try to connect my dots here. This is not going to be a very good line, but kind of gives you the idea. Now, you can see with this how only having 2 points probably doesn't give us as accurate an idea of where our graph is going to be as having 3 points like we did before. But again, it's another way that we can graph if we want to. And the whole idea of knowing where to fill in zeros usually makes evaluating the x and the y-intercept a little bit easier, because working with 0 helps to eliminate part of our equation. Alright, now finally, we're going to get to the point where we talk about slope-intercept form. If you understand how slope-intercept form works, graphing lines, graphing linear functions, linear equations becomes very simple. Alright, the key is understanding what the m represents and what the b represents when we get something in this particular form. Alright, the m and the b simply represent numbers. Alright, so I could say y equals 2x minus 4. The 2 would be in the place of the m, and the negative 4 would be in the place of the b. The m represents the slope of our equation, or the slope of our line. The b represents the y-intercept, or where is my graph going to cross the y-axis. Alright, now again, the whole idea of y here is a little bit interchangeable with f of x. So if you see something written in function notation, it means basically the same thing as if you have y equals mx plus b form. Alright, now here's an example of another function. It looks similar to what we worked with when we found the x and the y-intercepts to help graph. Now obviously, if we look at this particular function, we will notice that it is not in slope-intercept form. It is not in the form y equals mx plus b. So we need to get it into that particular form. Alright, so I'm going to rewrite what we start with down here. And the whole idea is, if we want to get it into y equals mx plus b form, we have to get the y by itself. So in this case, in order to get the y by itself, I need to take and add 4x to both sides. Alright, so over here, I will be left with my y. On the other side, I will have 4x minus 1. Now we're in slope-intercept form, and now it's quite simple to graph that particular equation. Alright, so I'm going to start with my y-intercept, which is negative 1. On my x-axis, on my y-axis, sorry about that, on my y-axis, because this is the y-intercept, right, I'm just going to go down 1 unit, and I'm going to put a point. That is the point at which my graph will cross the y-axis. Now I'm going to look at my slope. Now, we have a whole number for a slope. Slopes, like we talked about, are written as rise over run, or the change in y over the change in x. Alright, so I need to think about 4 as if it were a fraction. So if you ever have a whole number, we can always assume that that number can be written over 1. So my rise is 4, my run is 1. Alright, so what I'm going to do is I'm going to go up 4 units, 1, 2, 3, 4, and I'm going to go in a positive direction 1 to find my first point. And again, remember, if you have a positive slope, that also means that you could technically have negative over a negative. Alright, so in this case, I'm going to go the opposite direction, and I'm also going to go down 1, 2, 3, 4, and I'm going to go to the left, or a negative direction, 1 unit to arrive at my third point. Okay, this gives us a pretty good idea of where my graph is going to go. So I go ahead and draw my lines in, and after a fairly simple process, we're able to tell what that graph is going to look like. Same idea right here. The only thing that's a little bit different with this one is, in order to get it into our slope-intercept form, we might have to do a little bit more manipulation or a little bit more work to get the y by itself. So again, I'm going to rewrite the equation that I'm given, and I'm going to work to try to get the y by itself. So to start with, I need to get the x out of there, so I'm going to subtract x from both sides. When I subtract the x from the left side, I'm going to be left with 3/4 y, and that is going to equal negative x plus 6. Alright, now unlike the last problem where that was all we had to do to get the y by itself, here's a little bit different. Alright, I need to get rid of that 3/4 that is being multiplied by my y. So in order to do that, I could divide by negative 3/4. Usually in math we don't like to divide by fractions. We prefer to multiply by the reciprocal. So instead of dividing both sides by 3/4, I'm going to multiply both sides by 4/3. Now, this is the key to this particular problem that a lot of people make a mistake on. I have to take everything on both sides of the equation times 4/3. Obviously, on this side, when I multiply a number by its reciprocal, I'm going to get 1, or basically I'm just going to be left with y. On the other side, I need to take that 4/3 times both the negative x and times the positive 6. So when I take the 4/3 times the negative x, I'm just going to get negative 4/3 x. When I take the 4/3 times 6, just becomes a little bit more tricky. All right. If I'm taking a fraction times a whole number, again, I want to think about that whole number being over 1, because the whole idea of multiplying fractions is I take the numerators times each other and the denominators times each other. So in this case, to start with, I'm going to write this as 24/3. Now, if something's written in fraction form like that, it basically means we're taking the top and dividing it by the bottom. Right? In this case, 24 divided by 3 is going to give us 8. So when it's all said and done, I had to do a little bit more work, but I still get to something that's in slope-intercept form. So just like the last situation, I'm going to go up 8 on the y-axis and put my y-intercept. All right. Then I'm going to look at my slope. I wrote it as negative 4/3. That basically means the same thing as positive 4/-3, which just signifies that I can go in two different directions. Now in this case, I'm probably going to want to stick with the negative 4/3 because I don't have a whole lot of room on my coordinate plane to go up. So I'm going to count down 1, 2, 3, 4 spaces, and I'm going to go to the right, or in a positive direction, 1, 2, 3, and get somewhere in here. And then, like I said, instead of going up from my original point, spatially it makes more sense to go down. So I'm going to go down another 1, 2, 3, 4, and over 1, 2, 3 to get my next point. Again, I'll draw my lines, and that gives a pretty good idea or indication of what my line should look like. All right, the very last thing that we need to talk about is what happens when we get a horizontal or vertical line, what the equations for those would look like, and then, specifically what would happen if we were to graph those. This is an example of what they look like. I think most everyone's fairly familiar with what a horizontal versus a vertical line would look like. The big thing with this is it's almost kind of backwards. We always represent or think about up and down on a coordinate plane as being represented by a y. At the same time, we think about left and right being represented by an x. Well, it's backwards when we're talking about horizontal and vertical lines. As you can see from this graphic, a vertical line is simply just going to be represented by x equals a number. A horizontal line is going to be represented by y equals a number. Now, that might not make sense right away, but let's think about this for a second. Okay? And the lines that are given on this probably don't work the greatest because they're not on a set number. So if I think about this coordinate plane going by 1s in each direction, up and down, Okay, I could think about this right here as being -1. Okay, if that's the case, think about all the points that would happen to be on this line if I were to plot them going up and down. All right, the x value on those lines is always going to be the same, or I should say the x value for those points is always going to be the same. It is always going to be -1 regardless of where I put the point. The y values are going to vary a little bit, but the x value is always going to be the same. That's why we use x equals some number. In this case, it would be x equals -1 to represent the line that I drew in, because the x value is going to be the same for every single point on that vertical line. The idea is no different when we talk about horizontal lines. And again, I'm going to draw in one that's right on a coordinate grid here. All right, so we get a better idea. So if I call that value 1, the equation for this one would be y equals 1. Now again, it's a little bit backwards. You would assume that an x value would be associated with that. But again, if you think about all the points that happen to fall on this line, every single one of them is going to have a y value of 1, or a y value that's the same. That's why we use y equals a number, in this case y equals 1, to represent horizontal lines. All right? Now, something that's kind of important, if you have a vertical line, a line that goes straight up and straight down, okay, we think about slope as being rise over run. All right, well, in this case, the rise is going to go on forever. It's never going to stop going up. It's never going to stop going down. And it has no run. Okay, it does not move in either direction. So we could think about the rise in this case almost being like it's infinity, and the run being 0. Well, we know, and we talked about this in class a little bit, that you can never have a fraction where you have 0 on the bottom. All right, it doesn't work. Your calculator will give you an error. We refer to it as undefined. That's why the slope of a vertical line is undefined. At the same time, if you think about a horizontal line, all right, it has 0 run and an infinite 0 rise and an infinite amount of run. All right? So if you ever have a fraction where you have 0 on top of something, it doesn't matter what's on the bottom, the slope or the number, the output value in this case, is still going to be 0. So that's why a horizontal line has a slope of 0. Just something important you should probably try to remember as we move through some of this stuff. Okay? These lines are very easy to graph. All right? As long as we keep track of the fact that it's kind of opposite. We have x equals something, all right, that actually represents a vertical line, all right? So I'm going to find 2 on my x-axis, all right, and I'm basically just going to plot a bunch of points here to represent the fact that we would have a vertical line if it's x equal, all right? The x value is going to be the same for every point that's on this line, and I can finish by drawing in my line. Again, the slope of that line is undefined, okay, because we have an infinite amount of rise, but we have 0 run. All right, the other line, y equals -4, all right, is going to be a horizontal line. So what I'm going to do is I'm going to find -4 on my y-axis, it should be down here, and I'm going to just plot some points going across at that line. All right, horizontal line, can draw in this way. Right? Remember, every point that happens to be on that line is going to have the same y value, and that y value in this case is -4. Again, explaining why y equals a number actually represents a horizontal line. All right, that wraps up everything that we needed to talk about in this section. Similar to last time around, we're going to just got some worksheets that we can use to make sure that we're understanding what's going on here. So the worksheets can be found in the same place that the last ones were on my website. If you have any questions, make sure that you come see me and ask about it.